Hello everyone, and welcome to the pre-lecture for Chapter 17. Also, happy Halloween. So in Chapter 16, we learned about different types of sample surveys and how to take them and what's the best way to take them. Now in Chapter 17, we're going to use those sample surveys and estimate entire populations. The idea of using a sample to estimate an entire population is called inference, statistical inference. And normally, when we've been doing these types of problems, we know what our odds are. We know exactly what's in the box. However, now, that's what we're trying to find out. We don't know what's in the box. We don't know what the entire population is, but we do know a small sample. And we're going to use that small sample to estimate the entire population percentages. So for our example today, we are interested in looking at what percentage of girls ages 18 to 28 dress as cats for Halloween, or basically just anything in the cat family. So it could be a cheetah like myself, or a leopard or Catwoman, or just a regular cat. We want to know how many girls dress up as cats on Halloween, because apparently that's a pretty common costume for college-age girls. So, to conduct this research, I took a sample of 400 girls on U of I's campus, ages 18 to 28, and found out that about 20% of them dress as cats. But what we're really interested in is part A. We want to estimate the percentage of girls in the entire U.S. who dress as cats. So, knowing that that's what we want to estimate, and knowing that 20% of the girls from our sample dress as cats, what do you think we're going to use to estimate the population percentage of girls in the U.S. who dress as cats?
The results from our sample survey?
Right, exactly. That's what Chapter 17 is titled, using samples to estimate populations. So that's exactly what we're going to do. We're going to say, if we have to estimate the percentage of all girls that dress as cats, we're going to estimate the number that we got in our sample. So 20%. All right, so we said that about 20% of all girls in the U.S. dress as cats on Halloween. However, if we just said 20%, that's a pretty strong assumption to make. Usually we say 20% give or take some number. So that's what part B is asking. It says give or take what amount. So what do we usually use to find that amount of give or take, or that amount of wiggle room? Steve?
Don't we usually use the SE percent?
So that's exactly right. We're going to use the SE percent. Now to find the SE percent, we usually just use the formula. So does anyone remember what the formula for SE percent is? Wenli?
Is it SD over the square root of n times 100%?
Exactly right. It's the SD divided by the square root of n times 100%. But the SD of what? What are we talking about here? When we do these types of problems, we usually have a box, right? It's the SD of the box. So to calculate the SE percent, first thing we're going to do is draw our box. And so we're trying to figure out what percentage of girls dress as cats for Halloween. So we have either they do dress as cats or they don't. And this box that we're going to draw is for the entire U.S. population. So dressing as cats is going to be shown by a 1 on the ticket. Not dressing as cats is going to be shown as a 0. And so how many tickets are in this box? Well, we don't know the exact number of people in the U.S., but we know it's going to be a lot. We're going to have millions of tickets. But we don't know the exact number. And then we want to know what percent are 1s and what percent are 0s. This is what we're trying to figure out, but we don't exactly know that. We know what percent are 1s and what percent are 0s from our sample, but for the whole U.S. population, we're not sure exactly of the percentage of 1 to 0. That's what we're trying to figure out. So that brings us to the conclusion that we don't actually know our SD of the box, right? Because if we did the formula for SD, we would just have question mark and question mark as our percents of ones and percents of zeros. So does anyone have any idea of what we could possibly do next? We don't know anything about our whole population, but we need to use something to estimate this SD of the box. Wenli?
Could we just use like the proportion from the sample that we got in the survey? So like 20%, like for 0.2 would represent the ones, and then like maybe 0.8 would represent the zeros?
Yeah, that's a good idea. So we're going to use what we got from our sample survey to estimate what we have for the entire US. So if we were estimating from our sample survey, how many ones, what percent of ones would we have?
We have 20% ones.
Right, we'd have 20% ones, and then that leaves us with 80% zeros. So this is from our sample. So now we can calculate the SD. So the formula for the SD is the absolute value of 1 minus 0, the two numbers on the tickets, it's a 1-0 box, times the square root of the percent of ones times the percent of zeros. So just 0.2 times 0.8. So now we have an estimated standard deviation. We're using our sample to get that. So when we calculate this out, Celeste, what do we get for the sample standard deviation?
We should get 0.4.
0.4. So now we're one step closer to getting our SE percent. We have the SD of the box of the sample, and we're going to use that to estimate the box for the population. So plugging in our 0.4 for SD, now we have to plug in our N. And our N, remember, was 400 from our sample. We used 400 people in our sample survey, and then times 100. So for our standard error of the percent for the sample, what do we end up getting? Yes?
2.
2?
Yep.
Well, that's a nice number. So we have 2. So we have estimated our standard error of the percent for the population from our sample. So in parts A and B of our problem, what we figured out was that about 20%, give or take 2%, of girls in the entire United States dress as cats for Halloween. And again, this is just girls age 18 to 28. So now we've added a new part to our problem, part C, and it says, how confident are we? So to answer this question, we're going to use the normal curve. And we know that if a bunch of people took samples of 400 girls, so we know that 68% of them would lie within one standard error of the true percent. So we know this because if we have z-scores of 1 and -1, the middle area corresponding to that is 68%. So with our problem, if we wanted a 68% confidence interval, we know that we would get 20 plus or minus 1 standard error, and our standard error we found was 2. So that interval we would get would be 20 plus or minus 2, so 18 to 22. And a way to interpret this would be to say that we are 68% confident that our true population percentage is between 18% and 22%. So what if we wanted a 95% confidence interval? Meaning, what if we wanted that middle area in our normal curve to be 95%? What z-scores correspond to 95%?
Pretty sure it's 11.
Oh, Steve says it's 11. That's actually not correct. 11 is pretty big. We usually don't have z-scores up to 11. You want to take a second try?
2?
Yeah, it's 2 actually. So we have -2 and 2 as our z-scores that correspond to the middle area of 95%. So now if we're making that 95% confidence interval, we would say that we have 20 plus or minus 2 standard errors away from the true percent. So 2 standard errors, our standard error is 2, so 2 times 2. So this gives us 20 plus or minus 4, which is an interval 16 to 24. So now again, an interpretation of this interval would be that we are 95% confident that the true population percentage is in between 16% and 24%. So thank you for watching.